Okay, so welcome everybody. Can you hear me? Hello?
Yes.
Oh, okay, good. Just wanted to check because I didn't do the update. Okay, we are discussing finally generated module, and today I will prove this so-called Nakayama lemma, which is quite important. And I think I already motivated. It's basically an extension of the Cayley-Hamilton theorem. So what we had last time, let me recall that. So the technical tool is the following observation. R is a commutative ring. And I have a matrix, capital Z, an n by n matrix. Okay, so you know this over fields, but please notice the notion of the determinant also makes sense over any ring. You just define it using this formula, sum over permutations and blah, 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 just the usual thing. So this Leibniz formula. And then we defined the adjugate. So the adjugate, so what's that? So let me recall the definition. It's, I'm sure you, okay, sorry. So this is an n by n matrix, and the entry at the position KL is defined as follows. You have some sign. It's a bit, and then I take the determinant of the submatrix, which I denoted C, LK. And what is this? So maybe I make a picture. So if this is my matrix C, I'm going to remove the k's column and the lth row. So I remove this. Okay, so this was that. I get a submatrix, and this is the submatrix. So this is the submatrix here. Okay. Okay, and what we proved was this. Let me put the star here. The adjugate is almost the inverse of the matrix, if it has an inverse at all. So the adjugate multiplied by the matrix is the same if I do the multiplication in the other order. What I get is a multiple of the identity matrix, and the scalar is just the determinant. So this is the important observation from last time. Okay, and as I maybe let me recall, last time I also, you know this, if you have matrices over a field, and if the matrix is invertible, then this expresses Cramer's formula for the inverse of a matrix. Okay, so this shows the adjugate divided by the determinant of the matrix gives the inverse. Okay, but the point is, if I write it this way, it also makes sense if the matrix is not invertible. And moreover, it even makes sense over any commutative ring, and it always holds, which I showed. Okay. So actually, I indicated two proofs. The first proof would be to do the same as in linear algebra using Laplace expansion. But then I gave another argument which gave a derived, okay, this property from the known property over fields. Okay. Okay, so what do we do with this? So here is Nakayama's lemma. Okay, I don't want to have it in yellow. Theorem. In Atiyah McDonald's is 2.4, and this is Nakayama's lemma. As usual, if theorems are named after mathematicians, it's not quite correct. So apparently Nakayama said it's not due to him. It was known earlier, but anyway, it just have this name. So I have a finally generated A module. Finally. A module. So the A, as usual, is our commutative ring. Then I have an ideal of the ring. Okay, so this is in the field situation. You don't have this ideal, it's uninteresting. And I have a linear endomorphism, an A linear endomorphism, which I denote by phi. So please remember that this symbol stands for our module of A linear maps from M to M. Okay. Such that, okay, so there must be a property relating to the ideal, and this is the following: the image of my endomorphism lies in the submodule A times M. So, okay, so these are all the assumptions, and the point is then the powers of these endomorphisms satisfy a linear relation. So very much like the characteristic polynomial, and the coefficients of these relations lie in the ideal. So then there is an n natural number, and there are coefficients, sorry, a1 up to an in the ideal, such that, okay, now here comes the phi to the n. If I say to the n, I mean n-fold composition plus a1 phi to the n minus 1 plus etc. plus, okay, maybe let's do this. Let's put the last term separate just for the sake of clarity. I mean, what is an? Okay, if I want to be very precise, I should say an times identity. And this holds, this identity holds in my endomorphism ring. So this is the statement. Okay, often people don't even write the it, they just write an and interpret it as an element of the endomorphism ring. Okay, because the identity is the one in the endomorphism ring. Does it look familiar? This is a way of saying Cayley-Hamilton in a way. Okay, I don't, right. Okay, didn't define what is the characteristic polynomial, but the corollary of the Cayley-Hamilton theorem over vector spaces is that. Okay. Right. So now I'm going to give the proof, and there you will see the similarity even clearer, the similarity of the Cayley-Hamilton. Okay. So the proof is not very long. It's a relatively short proof, but I think it's very elegant. Okay, so what do we do? So I want to apply this statement in the yellow box, yes, but in which ring? What will be the commutative ring R that I use? And it will be the following ring. It will be a subring of the endomorphism ring, the subring generated by phi. Okay, so this is the point. So let me write carefully. Consider the ring homomorphism. So from AT, T is a variable, T is a variable. Okay, goes from AT to end AM. Okay, the point is, okay, T maps to phi, but I can write it in more detail. I say this polynomial in T is mapped to this expression. Okay. Right, so by this universal property of the polynomial ring, this is well-defined, a well-defined ring homomorphism, and the image is a commutative subring. Image, okay, which I denote this way, suggestive notation, is commutative subring. Subring of this endomorphism ring. Okay, has to be commutative. So only work in this ring. So now I'm going to set up, right. So when you, in linear algebra, when you define the characteristic polynomial, what do? You have a variable, maybe t times identity matrix minus, or times identity minus the endomorphism. From that matrix, you take the determinant. Now what I'm doing is essentially that. I'm just a little bit careful because we are not over field. But okay, I said matrix, but we don't have a matrix here. This is maybe a point. In linear algebra, you have a vector space, you choose a basis. But here the whole issue is this module may not be free. It doesn't have a basis, but it has a finite system of generators. That's our assumption. So let's give name to this system of generators. Let's say x1 up to xn. Let this be a system of generators of my module. Okay. So I have this list of generators. Now I can define a matrix. Okay, there are elements aij in my ring A such that, okay, what do I do? So phi of xj is the sum. Do I do it right? No, I didn't do it right. I want to have xi here. Sorry. And I sum over j, and I have aij xj. So this is exactly what you do when you define the matrix representing a linear endomorphism. It's exactly the same. Is it good? Yes, I did it. Right, it's good. Right. I think that's what I want. So rewrite this. We always have to be careful here whether I take this matrix or the transpose matrix. So let me write it. This is the delta phi minus aij sum over all j xj. Okay, so that's just a formal way of rewriting this. So the delta ij is the Kronecker delta. Okay, I hope you agree. Okay, where maybe, okay, maybe to be very clear, what is the aij? I mean, if I write it this way, the aij should be seen as an element of my ring. So let me say this, where aij is interpreted as an element here. Okay, viewed as left multiplication. I mean, left multiplication is just multiplication, but it doesn't matter. It's all commutative. With this. Okay, so. Okay, so this is an identity here. This is an identity in this subring. Good. So now comes the matrix psi. Matrix psi. So maybe okay, there's a space here. It has the entries psi ij. The psi ij will just, okay, I write it in a second. The matrix is over this ring. So psi ij is defined as this expression. It's exactly the matrix entry, sorry. So this is psi ij. Okay. Okay. So this is our matrix. Now we apply what we have in this yellow box. Okay. Now we apply this to this matrix. Okay. So basically we try to write the inverse. Okay. Even though there is no inverse. So we will look at the adjugate. So let psi twiddle be the adjugate of psi. So it's a matrix, okay? Now we just, okay, Okay, what I want to do now is this, what I have here in yellow, I just write this down, and let me write it down explicitly with the indices. Then I think there will be no uncertainty of what I'm doing here. Okay, I don't want to be too formal here. So now so what we have is this. Psi ij sum over j evaluated at xj equals 0. Because this just expresses this, okay, this. Right, here I write psi ij, which actually, maybe it was confusing that I had this, maybe I should have put here parentheses, okay, to be right. So I have this. Okay, so now I multiply. On this, we get for all k, we get, let me write it. It's kind of hard to talk about this. So I multiply from the left with psi twiddle ki, and I multiply over I. Of course, I will get 0 because all these sums are 0. But here I can reorder first sum over j and then over I. Okay, then I get this. Okay, pull this out, evaluate at xj. Okay, it could be done more elegantly with matrix calculus, but because this is a, maybe if you work over any rings, maybe clearer to it explicitly. Okay, now our property star, okay, maybe it should be yellow. This yellow star, okay, which is important. This gives this formula. Okay, it says, okay, here I have a matrix product. Okay, the adjugate multiplied with the matrix psi. I get the entries kj. So this is delta kj times the determinant of psi. So this is just expresses this property star, written in coordinates, okay? If k different from j, it's 0, otherwise it's just the determinant of psi. Okay, so now, okay, that's what I have here. So this is this. Okay, so if k is different from j, there is no information coming from this equation, but when k equals j, then this is the determinant. So what I see now, for all k, the determinant of psi, if I evaluate it, because this is in the ring A phi, if I evaluate at k, xk, I get 0. Okay, and this means, okay, this thing, okay, is in A phi, and then this must be 0. So this implies that psi equals 0. Here. Right, because maybe, I don't know, this thing, this determinant of psi is an endomorphism. Okay, it's a linear combination of powers of phi. It's a linear map from M to M. Okay, and this map evaluated that all generators xk vanishes. So the map is 0. It's the 0 map. Okay, it's the 0 map. Okay, now we are almost done. The only thing that remains to do is to see, what is this determinant of psi? Now we just expand it. Where was the psi? Now we do the same trick as we do in linear algebra, where you see in linear algebra, when you have this matrix and you take the determinant, what you get is the characteristic polynomial in the phi. Okay, now just do this. So you expand.
I have a short question.
Sure, yes.
I do not understand how we can conclude from the disappearance of the sum that the terms disappear, because we only have that the sum is 0, But how do we know that actually the individual terms are 0? I mean,
sorry, I don't understood exactly where, at which line exactly is the problem?
we have a line that begins with 0.
Yes,
There we have 0 is equal, if we replace, is equal the sum over all j over determinant evaluated at.
right. Okay, but you agree with this line?
Yeah, I agree with this
Okay,
line.
but now comes the star. Okay, let me go back, but this is the non-trivial step. Let me go back. What was the star? This is this.
Okay.
So now what does this say? Okay, if you multiply the adjugate, here it's z, but this will be
yes,
psi.
okay, it's clear. And then we replace in the sum, we replace by the determinant.
Okay, we see the product of the adjugate with the matrix is a multiple of the identity matrix.
Yes.
But the scalar is just a determinant. So let's see. So now this is the.
Now we have that. That is. But now we replace after we have.
You agree with this as well?
Yes.
Ah, okay. Then it's
after that. My problem is after that.
Okay.
Because we have only that we sum disappears, but we don't actually have with individual.
That's right. So let me. I explained it, but I know this is confusing. Let me explain this again. So now what I take. Right. Okay. Okay, but right. No, I think this is still is, but you see that here. I mean, what did I have? I have K, right. I only get a contribution if J equals K. Okay, I sum over all J.
Okay.
If J is different from K, this is 0. So, right?
Yes.
So I only get the contribution for J equals K. So then.
Okay, in J is, no, J is not fixed. J is a running index. So, okay.
Right.
K is fixed. K is fixed.
But maybe,
okay.
Maybe I wonder whether I have a typo here.
No,
K is fixed. There should be no. Okay.
Okay, it makes sense because.
But let me see. I'm not sure whether I have a typo now. No, it's okay because I have the KJ here.
Yes, KJ, it's and then only one, and we have. Okay, I understand.
Right.
Okay.
Okay.
It works.
Okay, good. Thanks for asking. Okay. So now expanding. So expanding the determinant. So basically, according to definition, we don't have to expand it. I mean, in every detail, we just think of what is it essentially. So maybe I rewrite what was the psi. So the psi ij is delta ij phi minus this. Okay, so if I expand it, I get phi to the n times something. So it will be something of this form. Okay, and here is the identity. I just write Bn. Can you see what it is? I mean, maybe I make a picture. For instance, you have phi minus A11, phi minus A22, phi minus A33, okay? And then all this remaining minus, okay, I don't want to write everything. Okay, so, okay, you multiply the diagonal terms, okay? And then you don't want to write in every detail, just imagine mentally how you compute this. The point is, the only information that I need is about where do the b's lie. So some of the coefficients are easy to explain. So the B1 is up to assign the trace of Aij. And for instance, the Bn is up to assign the determinant. I assume you have seen this in linear algebra. And then you imagine how the others look like. But the point is now I claim all these B's lie in my ideal. We have all BI's lie in my ideal. Let's, at least it's clear if for the B1, because it's the trace, it will be the sum of the diagonal matrices. You know, all the Aij are in I, okay? So maybe I write it here. The Aij are in my ideal. Here is the product. And in between, you have to imagine how do the B's look exactly, then you see the line in the ideal. Because it's always a sum of products, and in this product, you have at least one element of the ideal times something. Okay. So then, this is the proof. Now I have my relation. This is 0, okay? This is 0. Put it in yellow. This is 0, and it has this form. Questions? So you see, it's I don't know which proof of the Cayley-Hamilton you learned, but this is one proof, a short one, and the point is you don't need that you have a basis. You just take a system of generators. Okay, you don't need a basis, and you don't need to know this relation about the inverse of a matrix. If you replace the inverse by the adjugate, you don't need to know that the matrix is invertible, because that could be a problem. Okay, you don't even to know that you are over a field. It's just fully general. Okay. Right. Okay. So this is yeah. This is a non-trivial result, I would say, Nakayama. It's an important insight because there is something entering here in this proof. It's not trivial. Okay, there are a number of corollaries, and okay, let me put them in the usual order. Some of these corollaries were maybe a little bit hard to remember, but I do it anyway. So there is corollary 2.5 in Mattia McDonald. So this you get when you apply the Nakayama lemma. Oh, by the way, if you go to the literature and you look Nakayama lemma, you find all kinds of different statements. So, but I think the one that I coined, the name Nakayama lemma, as this is the one I can remember best. So for me, it's that the Nakayama lemma. So now I apply this when phi is the identity. And what do I get? I get the following statements. So let M be finally generated A module. A is an ideal of A such that, okay, AM, this submodule is a submodule of M. This should equal M. Okay, then statements, there exists a D in the annihilator of the module M with the property that B is congruent to 1 modulo the ideal. Okay, so this is maybe a funny statement, but the proof is very short. So I apply the theorem to 4 to phi equals to identity. Okay, then I get A1 up to AN, my ideal, such that, okay, now all the powers of the identity are the identity. So let me write in detail. Okay, I don't write identity to the n, blah, blah, blah. It's just identity. So this means, so, okay, I write it this way, 1 plus. This times identity equals 0. But this means that this multiplied with x is 0 for all x in M. Okay. Because this is how we interpret this. We interpret this element of the ring as the multiplication with this. Okay? Or if you don't like it, you just take this and evaluate at any x in M. Then you have this. Okay? Okay, now we just call this B. This is our B. B times every element, any element of the module equals 0. So B is in the annihilator. B is in the annihilator. And clearly B is congruent to 1 modulo our ideal. Okay, because it's 1 plus the sum of elements of the ideal. Okay. Okay. Right. So as I said, this is kind of difficult to remember. So there is another typical conclusion. I want to also explain it. This is Nakatia-MacDonald's proposition 2.6. So this is, what do I want to do? So when we want to apply this, okay, so this corollary is often applied in a situation where you want to prove that the module is actually 0. You want to show that the module is 0. Okay, and this you can do when you have these assumptions, and the A, this ideal A is not just any ideal, but it's contained in the Jacobson radical. Now, maybe you forgot what this was, the Jacobson radical. So the most important example is the case where the ring is local. Okay, when the ring is local, then you, by definition, you have just one or exactly one maximal ideal, and this is the radical. But in general, if you have a non-local ring, the Jacobson radical is the intersection of the maximal ideal. Not too important for us, but okay, let me state it because we get it for free. So M is a finitely generated A module. A is an ideal of A contained in the Jacobson radical. Okay, maybe call it R of A. Then the point, then we have this implication. If we can show AM equals M, then this necessarily implies M equals 0. Okay. And the proof, extremely short, we use our corollary above, corollary 2.5. Just gives the existence. We are exactly in that situation. So it gives the existence of a B in the annihilator of the module. Okay, the thing that, okay, such that B is congruent 1 mod A. Okay, now we have to remember what was, okay, how is this Jackson radical characterized? So the point is, if you have an element, so the B, okay, so B is 1 plus an element of this ideal. And by the characterization of the Jackson radical, that was proposition 1.9 in a T.M. This, okay, I can write it. This is a unit. Okay, so this is, okay, that's always. If you have a 1, you add an element in the Jackson radical, you get a unit. Think of the special case. You have 1 of a local ring. You have 1, you add an element in the maximal ideal, you get a unit. Okay, then I'm done. So I have now B, it's a unit, it annihilates the module. So the module must be 0. Okay. So okay, from M equals 0, we get M equals 0. Okay. So I admit, honestly, myself have trouble remembering all these statements. So they are kind of weird in a way. But okay, but the first theorem, this one, I don't know. This one I think is easy to remember. This makes a lot of sense to me in a way. The others are sometimes a little bit weird. Okay, but here is one special case that I think is at least easy to remember. So let's do this. Okay, think of this example. A is local, a local ring. I have a maximal ideal M. Okay, a unique one because it's local. And M is a finally generated A module. Okay, a very common situation. And then the point is this, if I can write it as this implication, so this is used very often. If M is not a zero module, then I get a proper submodule here. So this is very useful for induction proofs, okay? You have a local ring, a module, which is not a zero module, then this, okay, module here, M times M is a proper submodule. This follows from that. You see, I just, okay, I go to the contraposition, okay? And for A, I take the maximal ideal. Okay? So this is something, I think, maybe let's put it in yellow somehow. I think good to remember. Good. So there is another corollary. This is, okay, also useful. Let me write it, but it will be basically for free. Corollary 2.7. Right, so let me just write it. M pilot generated A module. Then I have a submodule, M of M submodule. And I have an ideal A. It's always this generality. It's contained in the radical ideal and the Jacobson radial contained in Jacobson radical, okay, of A. So as before, but now N is a submodule. The point is this: if let's say you can show that M equals AM plus N. So you have your submodule N, but you also have this submodule. And you assume if you add them up, you get everything. Then you can infer M equals N. Okay. And the proof is basically for free. I just apply this proposition. Here it is. Okay. I apply this to the factor, this proposition. I apply to the factor module M mod N. Apply proposition 2.6 to M mod N. Because if I have this and I go to the factor module, then I have factor module equals A times factor module. And then I apply the proposition. Factor module equals 0. This means this. Okay. Okay. So, right. So this is a bit abstract because it's so general, but now let me move. Okay, now let me move to the situation of local rings. This is a very important situation, and there we will get a very nice result about the minimal number of generators of the maximal ideal. So, okay, important applications, important application to local rings. Okay, so what is the setting? Oh, what happens? No, it cannot. Ah, sorry. I started. not on page 1. So I used up already my boards if you want, but I need a little bit more space. This going to be ready in a second. Okay. Okay. So what is the setting? So a local ring. M, its maximal ideal. Then I give a name to the factor ring, okay, which is a field. So A mod M, okay, is a field. So this is the residue field. So these notations are very standard. Okay, so now I have an A module. Let be. The idea is I want to apply what I know about vector spaces. So I want to, in a way, I would like to replace this module by something related to it, which is a vector space. So I look at the following factor module. View, can view. So what I do, I have M, and then in M I have this submodule MM. This is a submodule, and I take the factor module. This is an A module, but I can view it as, can view as A mod M module. Okay, why? Because, okay, because, okay, we had a general principle, but you see directly my M, by which I divide the ring, is in the annihilator of the factor model. Okay, so this is just well defined. The point is just this. Yeah. Okay, how would you define the multiplication here? You take an element here, you pick a representative, an element of A, and then you have the multiplication here. And this is well defined because if you pick an element in the maximal ideal and you see what it's doing here, just the zero map. Multiplying with an element of M gives here the zero map. So this is well defined. But the good thing is now, this is K. Okay, let me do it in yellow. So this is K. So this is a vector space. So this is a K vector space. Okay, so we have a vector space here. And if our module M as an A module was finally generated, this vector space is also finally generated. Okay, basically by the same elements. So it is a finite dimensional vector space. It has a dimension. So now the question is, what is the meaning of that dimension for the module M? Okay, and so I can make this clearer. Okay. So what happens? Okay, let's, so if M is finally generated A module, then this thing, this quotient object, is finite dimensional, finite, let's write it, dimensional K vector space. K vector space. So now let's look at the canonical projection, the canonical morphism from M to the factor module. Let's just put, okay, to denote it, let's just write it with this bar. Okay, so and we get the following interesting application. Right, I want to know, it's about the following. you see this module M, in general, it will not be a free module. I don't have basis, but I have a finite system of generator. And then I may wonder about the cardinality of the system of generators. Okay. If you have a system of generators, you can get a minimal one by throwing away those that you can throw away. Okay. Minimal can mean several things. Minimal can mean minimal with respect to inclusion. Okay. But it may be that you have two minimal system of generators of different cardinality. How can you know that this is not the case? Okay. And here we can prove now over a local ring, this is impossible. Okay. All minimal system of generators of the module have the same cardinality, and this is exactly the dimension of our vector space here. So this is really nice. Okay. Okay, so proposition 2.8. I just say under the above assumptions. Okay, so if, so this is, let's say I have elements x1 up to xn in my module such that the images in the factor module generate the factor module. So they generate the K vector space. M mod MM. Okay, and then the statement is then x1 up to xn generate M. Generate the A module M. Ah. So I think it's really important to have this. Okay. So if you want to check that these are generators of the module, it's enough to go to the residue class to this vector space and check it there. And why is that the case? Well, the proof, it's basically our, okay, we are going to apply our corollary 2.7, which is, we're going to use this thing. Okay. Right. So let me do it. So let N be the submodule generated by the Xi. By x1 up to xn. So I have the submodule N, and I want to prove N equals M. Okay. Then, so I claim we really have N. Okay, maybe I write it this way. M is the sum of N plus MM. Maybe I give a line of argument. So what do I have? I have here my canonical projection. Okay, and I compose it, or just with the inclusion. Here is my inclusion projection. Okay, so what happens? Xi goes to Xi. Yeah, goes to Xi bar. And right. So this is surjective. Do you see?
A question about notation. Right. With such a special error, you always denote inclusion, right?
Yes, the hook error is an inclusion. That's right.
Okay.
Okay. Right. Okay. No complaints. Now I apply my corollary 2.7. And this gives me, hopefully, M equals N. Maybe let's go back to it to check in case we have forgotten. So we are here. The point is, I just apply this with where A is the maximal ideal in my local ring. So I'm in the Jackson radical. I have M equals mm plus n, therefore equality. So this is a bit right. So you see, maybe this corollary 2.7 is a bit weird, but this is a really nice application. Okay, proposition 2.8. Maybe a corollary, also nice to remember. I said it already. Under the above assumptions. Okay, let's say let's call D the dimension of this vector space dimension. Okay, then I can say M can be generated by D vectors, can be generated by D vectors. Okay. But not by less. Maybe let me write any minimal generator, system of generators, minimal. Any minimal system of generators of M has exactly the elements. Exactly the elements. Minimal, I mean, with respect to inclusion. Okay. So this saves a little bit this nice result from linear algebra. All bases of a vector space have the same cardinality. And here you have something which corresponds to that. Okay, you see that this is important, right? Questions on that? We will have some examples in the exercises, I think, on that.
Couldn't it also be that that we need less generators for M than we need for the vector module?
Less? No. I mean, the number of generators that you need for this vector space is D, okay? You cannot have less. Because, okay, this is the trivial direction. If you have, okay, we always have our surjective homomorphism. Okay, maybe this is subjective. Okay, if I have generators here, let's say 4 that generate M, you just map them. Okay, maybe I should be x1 map to xn. If they generate, then these images also generate, right? So you cannot have. Is it clear? This is the trivial direction.
Yeah, sorry. Yes.
And the other direction is the non-trivial one, which requires the Nakayama. Okay. Okay. So no questions, apparently. Okay, I think we will have some nice applications of Nakayama in the exercises that have to do somehow. They have the flavor of it. For instance, okay, something I'm not prepared, but for instance, you want to show this. A is your ring, okay? And you know, now you view this as A modules. Let's say you have A to the M is isomorphic to A to the N as A modules. Okay, so maybe I will put this, let me put it as exercise. I'm going to suggest it to Marco. Then you can infer M equals N. So if you think this is trivial, if the ring A if you allow non-commutative ring, this is wrong. For commutative rings, it's okay. Okay.
But the only assumption is A is commutative ring, right? It doesn't have
yes
directly to do with anything above.
Nothing.
Okay.
Okay, now if you think about doing this, of course, there is no local ring here. I mean, you want to use, say, okay, you want to maybe, right. So what can we do? But the commutative ring, I mean, by the way, it's wrong, the statement. I just tried to prove it and then I realized the proof fails because I need to have a maximal ideal. Okay, so that's the idea of the proof. You need to have a maximal ideal. And then you look at everything modulo the maximal ideal. Okay, and then you are over, right? And then A mod M, actually, I'm thinking, do we need Nakayama? Right, I don't think, but maybe M is not a good thing. M is always used for, let me change notation, because M, I like to have M for the maximal ideal. What are good letters? R and S, maybe. R and S. Okay, let's do the exercise together. Okay, proof. So actually, I don't need Nakayama. Nakayama is for more sophisticated stuff. You do this. Let M be a maximal ideal of A. It exists, okay, because A is not 0. And then you, okay, you take everything mod M. So infer get. Okay, maybe there is a little step here that I leave to you. Okay, you check yourself that this is a valid conclusion. Okay, maybe check this, that you can actually conclude this. But here we have a field. Okay, and then you use linear algebra to infer R equals S. Okay. Right. Okay. Actually, it is not it's not Nakayama. Okay, but right. Good. Then let's start with a new section. A new section. So section 2.6, it's exact sequences. So I follow, okay, I follow Attia MacDonald. Actually, this is a very formal thing, and but it's useful. Okay, it's useful, but a bit dry. Okay, basically we introduce some language. Okay, so it leads to directional homological algebra. So what is an exact sequence? Probably you have seen it. Do you know already what is an exact sequence?
No.
No. Okay, good. So then let's do it. So, okay, a sequence of modules. A sequence of A modules and A linear maps. Okay, it's always good to have diagrams. So from mi minus 1 to mi, you have a linear map, which I denote fi, and then you go 1 to mi plus 1. This is fi plus 1. And you think that just goes on as long as you wish, and maybe also, it may also end, but okay, you have such a finite or infinite sequence. So this is called exact. Exact. Okay, if following holds. The image, if for all I, the image of Fi equals the kernel of Fi plus 1. So so maybe this needs a little bit of motivation, I realize. Okay, let me move it down. Okay, I try to explain. Okay, note. Okay, so okay, I want to put the remark. I say the following is always true. The image of Fi is always contained in the kernel of Fi plus 1. Always true. Why? So let's take some color here. It's best to, okay, this is the beginning of diagram chases. So an image of Fi, how do you get it? Okay, you get an element here. Maybe I don't even give it a name. Okay, it's an element here, but it comes from an element here. Okay, no, I'm saying this is not even true. Okay, I'm going to correct. Sorry. So what I want to let me correct it. If first, so this is a remark. So let me, okay. So sorry for the confusion. Here is the remark. I have the idea it will help a little bit to explain the concept. So we have a sequence here. So now let's assume we have the following. If we first do Fi and then Fi plus 1, so we compose these two maps, we get 0. Okay. What I say, if this is the case, then the image of Fi is contained in the kernel of Fi plus 1. Now let me explain why in the picture. Right. So this element here, okay, color, is in the image of Fi. Okay, so it comes from something. I have here something, it maps here. Okay, so if this element, I map it further, okay, I get here. But this element here must be 0. Because how do I get it? I get it by applying this composition. First this and then this. But what I'm saying is this composition is 0. Okay. I could write it formally, but can you see that? Shall I write it formally? Not necessary. I mean, yeah.
It's clear.
It's thank you. The problem is with these arguments, they are very trivial, but if you write everything, it can be really confusing. You have lots of notation. So this is a situation, maybe I want to motivate a little bit where this occurs. So often so where does it arise first? I think this idea comes from topology. So when I don't know whether you have seen it, where algebraic topology actually, where these maps here mean take boundary of something, boundary of a complex or what. And the boundary of a boundary is always 0. So in algebraic topology, you often have such sequences with this property. Okay. And then, so you always have this. And then you want to know how far are these two vector spaces apart. And what you do, you look at the vector space, you say this modulo this module that you get, this is called a homology module then, okay? And the best situation is when the homology equals 0, it means you have equality here. And this is exactly this. Okay, this was just talking and hopefully motivating a little bit. So exact sequences are kind of the best sequences, okay? Right. So, okay. Okay, and then, oh, maybe I should say, okay, let me improve my notes. Okay, I want to say is exact at I if, sorry, I want to say it's exact at I if this holds at the position I, and if it is true for all I, we say the sequence is exact. The sequence exact if exact at all. Exact. Maybe I rather say at I better say MI. Sorry. Okay. Yeah. So let's look at some special cases. Okay, so for instance, this sequence just has two terms, m prime and m, a map, and let's put at the left end, left end, put the 0. So 0 is also is a module, okay? It's a 0 module, and the map from 0 to m is of course the 0 map. Okay, so what does it mean that this sequence is exact? Well, it means the image of this map, but this is the 0 map. So 0 equals the kernel of f. So it means the kernel of f is 0. So this says f is injective. So this is something you should remember. So this is a funny way of expressing that a map is injective, but it's very, very common. Okay. Or I can do this. I go from m to m2 prime with the map G, and then here I put the map, everything goes to 0. Of course, there is just one such map. And this being exact, what does it mean? Well, it means the image of G is the kernel of this map. But the kernel of this map is M2 prime because it's a 0 map. So this means G is surjective. Okay. Okay. As I said, I just introduced in this section, basically I introduced language. Okay. Okay, now a short exact sequence. So, okay, this appears very often. So let's say I have M prime, M, M2 prime. Here, this I call F, this I call G, and then I finish it by putting 0 here. So this is called a short exact. Okay, this is a short sequence. Let's see when is this, what does it mean that this sequence is exact? Okay, exact. If and only if. Let's see. So it should be exact at all modules. So exactness here means F is injective. Exactness here means G is surjective. So let me write this, F injective. And G is surjective. So this is an end, but I don't write it. And the last, okay, this, okay, if I write it out, the exactness at the middle module means image of F equals kernel of G by definition. But this I can see in the following way. Okay, maybe I need a little of space. Okay. Because there was also this notion of the co-kernel. Let me put it maybe in green. So you divide here M by the image of F. So this is called the co-kernel. The co-kernel. We had it already. And so here is my canonical map. Right. Now I claim the exactness at this middle position I can express by saying I have an isomorphism from the co-kernel of F to M2 prime. This is an iso, okay. Isomorphism. Okay, so I want to here an isomorphism. Right. Because, yeah. This needs a little bit of thinking. You need one inclusion you need in order to have this dotted green map to be well-defined. The other inclusion tells you not only well-defined, but injective. And why is it surjective? Because it's the G. The G is already surjective. This I said here. Okay. So, okay, people that work with these diagrams a lot, they just know that, what this means. Okay. So these are called, okay, short exact sequences. And not in green. Sequences. And the point is, whenever when you have a long exact sequence, you can break it into small exact sequences. So maybe let me also explain this. Any long in quotes, because I didn't formally define what it is, but it's just a bit longer. Exact sequence can be broken or can be split up into short exact sequences. So I explain here, there's not much happening actually. So let's see, let's assume I have this part of my sequence. It goes on. So this I denote Fi, this is Fi plus 1. So assume this is exact. Then I put Ni as the image of Fi. But the image of Fi, because of exactness, equals the kernel of Fi plus 1. Okay, so this is a submodule of Mi, and then I obtain, let's see. So here I put Ni, but the Ni is a submodule of Mi, so I can put here as a map the inclusion. So I could write it this way, but maybe I don't do it because people in homological algebra, they don't do this. They say they write it this way. Okay. This expresses that this map from N to M is injective. That's okay because Ni is a submodule. And here, right, what do I do? Here I put Ni plus 1. Yeah. And what is the map? Yeah, this map here is essentially, it's this map. Because this map goes to the, okay, this goes to Ni plus 1. Ni plus 1 of the image of Fi plus 1. So what I do here, instead of this, I just write what is the image. Okay, and this, of course, is then surjective. Okay. So what I showed, this exactness here and exactness here, I argued, and now, okay, and by construction, you also have exactness here. So this is an exact sequence, exact, and the short exact sequence. Okay, because that's right. There's nothing deep here. It's just a graphical way of expressing things. Okay. Right. Okay. So what can we do with that? Okay, now let's see what happens if I have such sequences. I have short sequences, and I kind of want to dualize it. So there are some useful observations. So let's do it. Given, how is my time? Okay. Given a sequence. Okay, if I say sequence, I always mean of A modules and A linear maps, of A modules and A linear maps. So, okay, goes, okay, I need more space apparently. Okay, so let's say M prime to M to M2 prime to 0. 0 is only at the right-hand side. Let's call this one. I have such a sequence. Okay. Now I assign to it. Okay, I pick any A module N. If N is A module, we get sequence. Okay, so hom. Right. So when I write hom, actually I mean hom A, but I don't want to write all ADA all the time. Okay. The module of A linear maps. Remove the A. I go to hom M N. I go to hom. And here I have M prime N. So you see it kind of the direction is reversed. Okay, and the point is, what is this map? So this is B bar, and this I denote U bar. And there is only one way to define these maps. I mean, one reasonable way. So any guess? So how do I define this B bar?
Some concatenation, but I don't know yet.
Somewhat?
Some concatenation.
Yes. Oh yeah.
But concatenation with
composition actually.
Yeah, that's what I mean.
Yeah. Let's put this always in color.
Concatenation with composition with inclusion.
Yeah, okay, let me explain. So I have my green module here, okay? And then I have a map here. I don't want to give it name, otherwise I have so many letters and it doesn't help. I think the point of this language is to use the diagrams. A linear map, the green one. And then I just compose it with V. I do first V and then this, okay? Then I get this. I get the linear map from M to N. This defines V bar, okay? It's composition.
But just a moment, we don't have any linear map from M double prime to N yet.
I assume so, because I want to, okay, then I need to write more.
I mean, we have to assume that there is one, right?
Yeah. Maybe here is alpha. And alpha, you map to the composition, here's alpha. Alpha composed with B, sorry. Okay, that's the definition.
Okay, right, of course.
So the definition is V,
yeah.
But this is not I don't find it very intuitive, but that's what it is. Okay. And if you have a map, I don't know, let's do another color, the dark green. If I have a map B here, it goes from, okay, this will be a map, not very visible. Okay. You just compose it. First U and then B. B bar beta is this. So you get the sequence defined by composing maps. Okay, and actually here I want to put the 0 and I call this sequence 1 prime index n. Okay, because from 1 I get this new sequence after selecting the module n. Okay, and then we have the following proposition here.
But you composed with Peter.
Sorry?
The other way around, you composed with Peter, not Peter composed with you.
Yeah, okay. I mean in the order, so it fits, right? Composing maps. I mean, this is not very precise, but there's only one way to interpret it. Okay, I wrote in color exactly the definitions.
Yes, but I mean, you have to interchange so that first you.
Yes, but yeah. Okay.
First you.
But you cannot compose the other way.
With V, you have to interchange with V.
Did I make an error? Ah, right, there is an error. It's right. Thank you. Just tell me there was an error. Should be green. This is this. Sorry, there was a typo. Okay, that's what you meant.
Actually not, but maybe I have to look at it more precisely.
Yeah. Okay. So what is these statements? This is actually, this is only the first part of proposition 2.9 in Idea MacDonald, and it says the following. Okay. Your original sequence 1 is exact if and only if this dualized sequence is exact for all n. For all n. Okay. So this is sometimes useful in proofs to have this. Okay. So I have 6 more minutes. Let me give the proof. So the proof, I don't know if you ever heard this. This is called chasing errors. So meaning that doing these proofs requires, okay, you don't need any intuition, but you need concentration. And you just follow the errors. There's usually only one possibility, you just check it. Some people also call it abstract nonsense. Okay, let's do the non-trivial direction. Okay, from the left to right is very easy. Let's do from right to left. So let's assume I have this. 1 prime is exact for every choice of n, and I want to prove that the sequence 1 is exact. So I will show you, okay? I will go through it. So let's do it in steps. Let's first check that B is surjective. So what was the V? Okay, it's unfortunately already far away. The V. Oh, it's that one. Okay. So how do I do it? So consider. Okay, I just write here part of my sequence. So this is the V. It goes from M to N2 prime. Now, okay. So what do I do? Now I choose my N. And how do I choose it? Here, I take the factor module N2 prime mod the image of V. So this is my choice of N. Okay. I can do it, okay? And then I have here, of course, my canonical map. Let's call this alpha. Okay. So what do I have? If I compose alpha with V, I get 0, of course, because I factor out the image of alpha of V. So this is strange notation. This is V bar of alpha. Okay, so I have V bar of alpha equals 0. But now I have, and now I use my assumption. My assumption is 1' n is exact. In particular, so here, this guy is exact. So V bar is injective. This is assumption, okay? So V bar is injective by assumption. And from that, I conclude alpha equals 0. But if alpha equals 0, the image of V equals M2 prime, and I have shown V is surjective. Don't ask me about the idea of this proof. It's just, it works. Okay. So that was the first example of chasing errors. That was a very simple one. Let's do, okay, I don't want to do too many of these things. It gets boring. But let's do this inclusion. The image of U contains the kernel of V. Okay, I have to show equality. Let's do first this. So, okay, I draw this, I always draw the picture. So I have M prime, M, M2 prime. This is called U, this is called V. So again, I have to choose a module, N, but this time I take this, M divided by the image of U. So this is now my N. It's a different N than before, okay? Maybe it should be different. Maybe an orange one. This is my orange. Okay. This canonical map, I denote beta. Okay, now let's see. If I compose first U and then beta, I get 0 as before. And so this is U bar of beta. So beta is in the kernel of U bar. Okay. Now, my assumption is, what is my assumption? Here, this sequence here is exact. So at which position I have to look now? Right. So I know the kernel of U bar equals the image of V bar. This is my assumption. Okay, so let me write it. So assumption, kernel of U bar equals the image of V bar. Maybe I should put parentheses everywhere. I usually forget. Okay. So what I now, okay, beta is in the image of V bar. So I find a gamma such that, okay, beta is V bar of gamma. So let me show it in the picture. Where is the gamma? It will be here. Okay, sorry, this should be N. I made a mistake. This is N. So then it makes sense because this is just a composition. Okay, first do V, then do the gamma. Okay, it's very abstract, but you just go step by step. So I have this gamma. And so I think now I should be done. I'm getting confused myself with these arguments. They are so trivial, but also unintuitive. The image of U is the kernel. How do I that? The image of U of the kernel of beta by construction of beta. And now I have shown, hopefully, that the kernel of beta contains the kernel of V. Yes. That follows. If an element is mapped to 0, it's because of that relation. Under V, it's also mapped to 0 under beta. So I wanted to show this, and I have shown it. Okay. Okay, but then maybe the rest I leave to you. Okay. This is similar. The other inclusion. Okay. Let's say similar. It's even simpler. Similar. Do it yourself. And finally, this inclusion from right to left is, it's also trivial verification. So somehow I have the feeling from these proofs, the only thing that you learn is that it is true. You don't see, what is the idea. But okay, this is homological algebra, by the way, but it's just the very beginning of it. Okay, so I think my time is basically through. So what I will do, this section is very, very short. So actually I'm doing this because this is helpful because the next bigger topic will be the tensor product of modules. It's a very important construction in commutative algebra. Maybe it's the most important construction in algebra at all, tensor product. It has many, many properties. And having this language of exactness helps, okay? So on Thursday, what I do first, but I do prove a little result in homological algebra, which is very important in topology. When you have a short exact sequence, okay, you have a map between two short exact sequences, and then you get your long exact sequences, which is, and I will do that, and I will show you the proof. It will be basically like this proof, but just much more complicated. Maybe you fill maybe 2 boards with explanation of arrows and you check it's true. You have to do it once in your life, okay? Right, so I do that on Thursday, and then we continue with the tensor product of modules. Okay, are there questions, or maybe I stop the recording now?